Welcome to G Fun Facts Online. Look up at the night sky. It is not a static canvas. Over the last couple of years, and stretching into 2026, it has become a theater of celestial violence and breathtaking beauty. The northern and southern lights have spilled far beyond their usual polar confines, painting the skies over places like Greece, Mexico, India, and the southern United States in vibrant shades of crimson, emerald, and amethyst. But these lights are not just atmospheric decorations. They are the visible footprint of a massive transfer of energy across 93 million miles of space. They are the glowing exhaust of invisible magnetic collisions. Today, we are skipping the long introductions and diving straight into the grand mechanics of the universe to explore exactly what is happening above our heads. To understand the aurora is to understand the physics of the sun, the architecture of Earth's magnetic shield, and the rhythmic 11-year heartbeat of the solar system known as the solar maximum. Let us start with the engine driving it all. Sun is not a solid body. It is a roiling sphere of superheated plasma, a state of matter where electrons are stripped from their atomic nuclei, creating a fluid of freely moving electrical charges. Because the sun is a fluid, it does not rotate uniformly. Its equator spins faster than its poles, a phenomenon physicists call differential rotation. Over the course of years, this differential rotation twists and stretches the sun's magnetic field lines, winding them tighter and tighter like a rubber band. This immense magnetic tension generates a cyclical rise and fall in solar activity. Every 11 years, the sun undergoes a dramatic transformation from a quiet, nearly featureless sphere during solar minimum to a chaotic, storm-battered state known as solar maximum. At the peak of this cycle, the sun's magnetic field becomes so tangled and unstable that it completely flips. Magnetic north becomes magnetic south, and vice versa. The visual markers of this extreme magnetic tension are sunspots. They appear as dark blemishes on the photosphere, the sun's visible surface. They look dark only because they are cooler than the surrounding plasma. While the average surface temperature of the sun is around 500 degrees Celsius, sunspots can be thousands of degrees cooler. This cooling happens because the intensely concentrated magnetic fields in these regions act like a giant plug, suppressing the convective upward flow of heat from the sun's deep interior. But do not let the cooler temperatures fool you. Sunspots are the launch pads for the most explosive events in the solar system. Let us talk about Solar Cycle 25. When this cycle officially began in December 2019, the consensus among forecasting panels from NASA and the National Oceanic and Atmospheric Administration predicted a relatively mild cycle. Early models suggested a peak sunspot number of around 115, comparable to the subdued Solar Cycle 24. But the sun had other plans. By 2023, it became abundantly clear that Solar Cycle 25 was massively overperforming. Sunspot numbers skyrocketed past 200, nearly double the initial forecasts. Scientists now believe that the actual peak of the smoothed sunspot number occurred around October 2024. But the chaotic energy of the solar maximum does not simply shut off overnight. We are currently experiencing a prolonged, highly active plateau, sometimes referred to as a double peak. This extended maximum phase has kept solar activity remarkably elevated through 2025 and into 2026. This unrelenting barrage of solar flares and geomagnetic storms has produced visually stunning consequences. In May 2024, an extreme G5 geomagnetic storm, the absolute strongest category on the scale, slammed into Earth, triggering global auroras seen by millions who had never witnessed them before. Similar severe storms followed in October 2024 and November 2025, constantly pushing the auroral oval far toward the equator. But how exactly does a twisted magnetic field on the sun result in glowing skies on Earth? It comes down to the sun's space weather arsenal, specifically the solar wind, solar flares, and coronal mass ejections. Even on a quiet day, the sun is constantly boiling off its outer atmosphere, the corona. This continuous stream of protons, electrons, and alpha particles is the solar wind. Traveling at speeds between 250 and 500 miles per second, the solar wind carries the sun's interplanetary magnetic field outward to the very edges of the solar system. Then we have solar flares. When the tangled magnetic field lines above a sunspot become too strained, they can undergo a process called magnetic reconnection. The lines suddenly snap and realign into a simpler, lower-energy configuration, releasing a catastrophic amount of energy. This is a solar flare, a brilliant flash of electromagnetic radiation spanning the entire spectrum, from radio waves to X-rays and gamma rays. Because flares are made of pure light, their energy reaches Earth in just 8 minutes. In November 2025, the Sun unleashed a massive X5.1 flare, and 2024 alone saw over 50 X-class events. While flares cause immediate radio blackouts by ionizing our upper atmosphere, they do not directly cause auroras. For that, we need mass. We need a coronal mass ejection, or CME. If a flare is the muzzle flash of a cosmic cannon, the CME is the cannonball. A CME is a billion-ton cloud of magnetized plasma violently hurled into space. They travel much slower than the speed of light, taking anywhere from 18 hours to several days to cross the gulf between the Sun and Earth. When a CME is Earth-directed, it acts like a giant snowplow, sweeping up the ambient solar wind and creating a massive shockwave. When this magnetized plasma cloud collides with Earth's magnetic field, the aurora is triggered. If Earth did not possess a magnetic field, the solar wind and CMEs would eventually strip away our ozone layer and atmosphere, leaving our planet as barren as Mars. Fortunately, deep within the Earth, a churning ocean of liquid iron and nickel acts as a geodynamo. The convection of these molten metals, driven by the heat of the inner core and the rotation of the Earth, generates a massive magnetic shield called the magnetosphere. On the sunward side, this shield is compressed by the pressure of the solar wind, forming a blunt boundary called the bow shock, much like water piling up at the bow of a moving ship. On the night side, the solar wind drags the magnetosphere out into a long teardrop-shaped tail, known as the magnetotail, which extends hundreds of thousands of miles into the darkness of space. Most of the time, this shield elegantly deflects the solar wind, but when a CME arrives, a complex physical interaction occurs. The key to a spectacular aurora lies in a specific orientation of the magnetic field carried by the CME. Earth's magnetic field points north at the equator. If the magnetic field of the incoming CME is also pointing north, it essentially bounces off Earth's shield, resulting in only minor disturbances and weak auroras. However, if the magnetic field of the CME is pointing south, a dramatic phenomenon occurs. Because opposites attract, the southward-pointing solar magnetic lines physically merge or reconnect with the northward-pointing Earth magnetic lines. This magnetic reconnection peels open Earth's sunward magnetic shield, allowing solar plasma to pour inside. The solar wind drags these reconnected field lines all the way back into Earth's magnetic hail. As more and more field lines pile up, the tension becomes unbearable. Eventually, they snap back together in a secondary magnetic reconnection event, operating much like a colossal slingshot. This snapping action violently accelerates electrons and protons, catapulting them down the magnetic field lines straight toward Earth's polar regions. Now we enter the mind-bending quantum mechanics of the aurora. As these high-energy electrons plunge toward the poles, they enter the thermosphere and ionosphere, roughly 60 to 400 miles above the surface. Here, the near vacuum of space gives way to a tenuous soup of oxygen and nitrogen atoms and molecules. When a high-speed electron slams into an oxygen or nitrogen atom, it transfers a portion of its kinetic energy to the atom. This energy kicks one of the atoms orbiting electrons into a higher, unstable energy state. In quantum mechanics, an atom cannot remain in this excited state for long. Within a fraction of a second to a few minutes, the atom's electron drops back down to its original ground state. To obey the law of conservation of energy, the atom must release the extra energy it absorbed by emitting a single particle of light, a photon. When billions of trillions of atoms undergo this excitation and emission process simultaneously, the sky erupts in a glowing, undulating river of light. The specific colors of the cosmic spectrum are dictated by two factors: the type of gas being struck and the altitude of the collision. The brilliant green we most often see is produced by atomic oxygen at moderate altitudes of 60 to 200 miles. When excited, oxygen takes about 3/4 of a second to emit a green photon. Because the atmosphere is relatively sparse at this altitude, the oxygen atoms have time to emit their light before colliding with another molecule, which would otherwise steal the energy without producing light. Higher up, between 150 and 400 miles, atomic oxygen undergoes a different transition that produces a deep blood red light. This is a forbidden quantum transition, meaning it takes up to 2 minutes for the oxygen atom to release the red photon. Only at extreme altitudes, where the gas is incredibly thin and collisions are rare, can the atom survive long enough to release the red light. These high-altitude red auroras are often the first things seen when a geomagnetic storm pushes the lights toward the equator. Down below 60 miles, we find heavier molecular nitrogen. It requires extremely energetic electrons, typically propelled by massive CMEs, to penetrate this deep into the atmosphere. When struck, molecular nitrogen emits blue and purple light. Furthermore, when ionized nitrogen regains an electron, it emits a vibrant pink or crimson glow. Because nitrogen exists at the lowest visible fringe of the aurora, it often paints a spectacular magenta border along the bottom of green auroral arcs. As we navigate through the spring of 2026, aurora watchers and space weather physicists are highly focused on the month of March. Historically, the weeks surrounding the spring and fall equinoxes produce the most intense and frequent geomagnetic storms. For decades, the mechanism behind this seasonal surge was a mystery. Why would the sun care what season it is on Earth? The answer was formalized in 1973 by geophysicists Christopher Russell and Robert McFerrin, now famously known as the Russell-McFerrin effect. It is entirely a matter of cosmic geometry. The sun's equator is tilted relative to Earth's orbital plane, and Earth's magnetic dipole axis is tilted by about 11 degrees from its rotational axis. Around the equinoxes in March and September, Earth's magnetic poles are oriented at a right angle to the flow of the solar wind. This specific tilt maximizes the geometric coupling between the Earth and the Sun. It essentially forces the southward component of the solar wind's magnetic field to perfectly oppose Earth's northward magnetic field. Because of the Russell-McFerrin effect, even a modest breeze of solar wind or a glancing blow from a minor CME can easily pry open cracks in Earth's magnetosphere during the equinox. Combining this maximized geometrical vulnerability with the lingering, highly charged output of the solar maximum means we are sitting in the ultimate golden window for auroral phenomena. But traditional auroras are not the only things lighting up our skies. Heightened scrutiny during recent solar maximums has brought a stranger phenomenon into the limelight, affectionately named STEVE. STEVE stands for Strong Thermal Emission Velocity Enhancement. Often appearing equatorward of the main auroral oval, it is a stark, narrow ribbon of purple-white light. When researchers attached spectrographs to analyze STEVE's light, they found a shocking difference compared to regular auroras. A normal aurora produces distinct emission lines, specific spikes of green, red, or blue, much like a neon sign. STEVE's spectrum, however, is a continuous, broadband wash of light. It looks less like a neon sign and more like the glow of an incandescent light bulb or a hot electric stove coil. Physics reveals that STEVE is caused by a subauroral ion drift. During severe geomagnetic storms, supersonic rivers of plasma flow westward through Earth's upper atmosphere. At altitudes of around 280 miles, this plasma flows at a staggering speed of 4 miles per second, generating immense friction. This friction heats the atmospheric gases to an astonishing 400 degrees Fahrenheit. STEVE, therefore, is not caused by electrons falling from space and exciting atoms. It is simply the thermal glow of a river of gas burning with atmospheric friction, a hyper-fast superheated ribbon of plasma native to our own atmosphere. Often accompanying the purple arc of STEVE is a series of vertical green stripes known as the picket fence. Unlike the purple arc, spectrographic analysis shows that the picket fence is a true aurora, but how it forms at such unusually low latitudes simultaneously with the thermal heating of STEVE remains one of the most exciting, actively researched mysteries in magnetospheric physics today. While it is easy to become entirely captivated by the aesthetics of the solar maximum, the physics that light up the sky are the exact same physics that threaten modern civilization. A severe geomagnetic storm is a kinetic and electromagnetic assault on Earth's infrastructure. When a massive CME compresses the magnetosphere, the rapidly fluctuating magnetic fields induce electrical currents in the ground, known as geomagnetically induced currents. Because the Earth is a poor conductor of electricity, these massive low-frequency currents seek the path of least resistance, which happens to be human-built infrastructure. They travel up the grounding wires of high-voltage power grids, overwhelming transformers. We have seen the consequences before. In 1859, the infamous Carrington event induced currents so strong they caused telegraph machines to spontaneously catch fire. During solar cycle 25, the hazards have evolved to match our modern technology. In January 2026, Earth was battered by an unusually rapid S4 solar radiation storm. Unlike CMEs, which take days to arrive, this event saw an intense surge of high-energy protons accelerated from the Sun to Earth in under 24 hours. Warnings were immediately issued to airlines to divert transpolar flights due to lethal radiation exposure limits, while astronauts aboard the International Space Station were forced to take shelter in heavily shielded modules. Furthermore, the heat dumped into the upper atmosphere by geomagnetic storms causes the thermosphere to expand outward. Satellites orbiting in low Earth orbit suddenly find themselves plowing through a thicker atmosphere. This atmospheric drag slows them down, degrading their orbits. In 2022, a relatively minor geomagnetic storm caused up to 40 newly launched Starlink satellites to prematurely burn up in the atmosphere. As we navigate the tail end of the current solar maximum, satellite operators must constantly burn precious fuel to keep their multi-billion-dollar constellations from falling out of the sky. As we stand under the canopy of the 2026 night sky, bathed in the glow of the Russell-McPherson equinox effect, we are witnessing the grand mechanics of the universe at play. The aurora borealis and aurora australis are not just beautiful anomalies, they are the physical manifestation of a protective shield doing its crucial job. Every shimmering green ribbon, every blood-red corona, and every purple-white streak of Steve represents a violent collision of solar plasma and atmospheric gas. They are the echoes of explosions that happened 93 million miles away. Solar cycle 25 has proven that our local star is deeply unpredictable. While scientists expect solar activity to gradually decline as we push toward 2030, the declining phase of a solar maximum is historically when some of the largest, most complex sunspots, and therefore the most powerful coronal mass ejections, actually occur. The Sun is slowly going back to sleep, but it will not do so quietly. For those willing to brave the dark, cold nights, the sky remains alive, a glowing, crackling testament to the magnificent, terrifying physics of our solar system. Look up, because the greatest light show on Earth is not over yet. Thank you for listening to G Fun Facts Online. Keep exploring and stay endlessly curious.